The initial release of EQR Opt for CST Design Studio was set up to optimize individual bandpass filters. Recently, we've added the capability to also optimize diplexers and multiplexers. So in this diplexer example, we have a Combline type equivalent circuit. These are our Combline resonators, resonated with these lump capacitors and coupled together with these capacitors. At the input and the output, we've simplified the circuit by using transformers. In a real filter, we would typically tap in and out of the first and the last resonators. To form a diplexer, we can take doubly terminated designs and connect them at a common junction through these series transmission lines. We choose the length of these series lines so that the input impedance of this filter gets rotated to an open circuit at the common junction in the passband of this channel. And likewise, the input impedance of this channel gets rotated to an open circuit at the common junction in the passband of this channel. This is probably the simplest way to realize a microwave diplexer. Our variables are set up down here in the parameter list, and we have variables for the tuning capacitors and the coupling capacitors, and also the impedance ratio of the transformers here near the common junction. The impedance ratio of the output transformers are fixed, and that ratio sets the return loss level for each channel. We set the optimization variable list here in CST Design Studio. We want to optimize on the resonator frequencies and the couplings and the ratio at the input for the transformer, and the same for the other channel. And then we also have a listing of the reflection zero frequencies. These are not optimized, or they're not set to be optimizable by the user, but they define the passbands for the two channels. So here's the first block of frequencies that defines a passband, and here's the second block of frequencies that defines the other passband. So if we launch the optimizer, there's very little detail here. It's really all contained in the way we set up the circuit file. There's very little for the user here to worry about. And if we look at the starting point for our optimization, these are both n equal 5 filters, so we expect to see 5 distinct return loss nulls in the passband of each channel. And here we only see 3, and here we see a hint of 4. But this is actually a good enough starting point for the optimizer to work on. We need 10 variables here and 10 variables here, and so we're going to optimize a total of 20 variables simultaneously when we do the optimization. So let's start the optimization running. And the first thing it needs to do is calculate the current error. And we see that over here in the progress box. And now it's going to cycle through all the variables using the forward difference technique to get the partial derivatives. So now It's found all the derivatives now, and it's doing an update to the variables. And here's our first set of corrections. And we're starting to see a pretty good response in both channels. And now we've finished the first part of the optimization cycle. And in the second part, the optimizer is looking for a new set of pole positions in the passband. And it'll try to improve the error by moving those pole positions just by a small amount. And now we're done. And clearly we have what looks to be an almost perfect equal ripple response in both channels of the diplexer. And now once we've captured both of the pass bands, it's quite easy to modify the bandwidth or to modify the center frequency of each channel. All we have to do is move the outermost reflection zero frequencies. The optimizer doesn't modify those, and it only displays the modified inner reflection zero frequencies after the optimization is done. We could add cross-couplings into one or both of the channels at this point by optimization. We can add a capacitive cross-coupling to this channel and get a transmission zero here. We can add an inductive cross-coupling to this channel and get a transmission zero here and improve the isolation of the diplexer. Another thing we might want to do is modify the return loss. Again, return loss is not a parameter that we set for optimization. We find that the optimization process is more robust if we literally fix the return loss level, in this case with the transformers. But if we want to modify the return loss level, all we have to do is change the transformation ratio out here. And if we analyze that, and we need to change the plot back to dB. And notice we've clearly modified the return loss level, and now all we need to do is re-optimize. This is actually a fairly major change to the element values. If you think about the low-pass prototype tables that you find in the literature, each table is unique for a specific return loss level. So by demanding a new return loss level here, we're forcing all the variables in that channel to change. And because there is some interaction between these two, some of the nearest element values in this channel may change as well. So we've made our first correction, and now it's stepping through and finding new partial derivatives. We could maybe save some time by not computing the partial derivatives at every step. That's something we've looked at on an experimental basis, but the safest way to do this is to compute new partials at every step in the process. And again, we've finished the first round, and now the optimizer will try to touch up the pole positions just a little bit. Clearly, we could save time by skipping this step. We can also set our error tolerance to a larger number here so that we do fewer iterations. And all of these things are useful in the initial stages, and perhaps we only need this kind of accuracy when we get down to the final design stages. And now we're done with our optimization. And we're at a new return loss level here. Instead of 20 dB, we're more like 25 dB return loss. And again, these diplexer designs are quite flexible. There really isn't a unique solution for any given problem. And in fact, the return loss levels don't have to be the same in all the channels. They can be different. So that's a quick introduction to the diplexer and multiplexer capability in EQROP CST Design Studio.